It's my pleasure to welcome Miriam Backens to DICE. Miriam is a permanent researcher at INRA in France, with previous postdocs at Birmingham and Oxford, where they've been doing a lot of work on quantum computing and classical computing. And they'll be giving us an introduction today about quantum computing. Floor is yours, Miriam.
Thank you. And yeah, it's a pleasure to be here at DICE. And yeah, as Desmond said, I'm going to do an introduction to quantum computing. So my plan is to talk a little bit about quantum computing in general, and then also afterwards tell you a little bit more in detail about the things that I'm specifically working on. But largely, the majority of it is going to be a sort of fairly high-level overview over kind of current topics in quantum computing. So first, kind of to give you a little bit of a, there we go. Background about me. So I grew up in Germany and then I moved to the UK for university, where I spent most of my adult life before recently moving to France. I did my undergrad in physics and then did a master's in maths, because that's where it turned out all the interesting theoretical physics was being taught. And then I had found out about quantum computing. And so I thought, well, I know the physics side of the quantum. So I went and I did a PhD in computer science. On something called the ZX calculus, which I'll tell you about a little bit at the end of my talk. It's a graphical language for reasoning about quantum computing. So that makes it kind of quite intuitive to use, which is useful when you're talking about quantum computing. And also, it's also formal, so everything, like, it's mathematically exact, and you can really use it to do proper rigorous science. As I mentioned, so I've done postdocs in Bristol and Oxford, and actually during my postdocs, I changed direction slightly. So previously I'd worked sort of entirely within quantum computing, but then during my postdocs, I applied methods and results from quantum computing to classical computational complexity. So this is kind of my answer whenever people ask me whether, like, what we're going to do if we never end up going to build an actual proper physical quantum computer. Well, the knowledge that we've gained in kind of pursuing this is definitely going to be useful anyway. We can take knowledge from the quantum computing world and actually also apply it in just talking about standard computers. And so that's not something I'm going to talk about in this talk, but I just thought I'd mention it because I find it's quite a neat sort of little thing. I was a career development fellow at Balliol College at Oxford for just half a year. Because as soon as I got the position there, or as soon as I started it, I got a job offer from a previously submitted application for a permanent position. So I then moved to Birmingham as a lecturer in computer science and spent about 4 years there. And so very recently I've moved to France as a permanent researcher at INRA, which is a state-funded research institute, and I think the official name is something like Digital Science and Technology. So it's largely computer science, but quite broadly constructed. So in general, in recent years, I've spent a lot more time talking to computer scientists than physicists. So it's a real pleasure to be here. But also, feel free to interrupt me at any point if I kind of get into too computer science-y a mode and things get, in case things get difficult to understand. So as a kind of motivation for what I'm talking about, so quantum mechanics, as people realized once we started building kind of computing machines, is really difficult to simulate on a normal computer. The reason for that is that in quantum mechanics, we have superposition of different states, and we also have entanglement. And so that means that the number of parameters that we need to keep track of in order to simulate a quantum system grows exponentially with the size of the system. And no one's found a way yet of getting around that when we're trying to run simulations. And so that means very quickly it becomes intractable to run those simulations even on a classical supercomputer. And so then in the 1980s, people came up with this idea, well, what if we had a computer that itself obeys the rules of quantum physics? Maybe that would help us simulate quantum systems in general. And so that was the start of this idea, really, of quantum computing. We've now got a quite well-developed field which has grown a lot over the recent years of quantum computation and quantum information. And so broadly, the sort of questions that we look at in this interdisciplinary field with people from physics, from computer science, from maths. I guess on the experimental side, you also get people from material science and from chemistry. So the questions we look at are, for example, what computational problems can we solve efficiently using a quantum computer, or more efficiently than using a standard computer, a classical computer. So that's maybe the sort of quantum computation part. On the more quantum information theory side, we've got how can we use quantum mechanics for other tasks that aren't sort of directly computation but are very closely related. So certain communication tasks, sending information between two parties, either more efficiently or more securely, cryptography, and also others. And then, of course, on the more practical experimental side, how do we build the devices that we need for this sort of stuff? And again, there's been a lot of progress on these things in recent years. So actually, on the communication and cryptography side, that's maybe something that's already got the most progress. So there are devices on the market that you can buy that do quantum cryptography, quantum key exchange. So they're being used by some banks, for example, to secure communication between different branches. But on the side of quantum computation, which is the one that I'm working on, we've also made a lot of progress. In recent years, we've had sort of experimental proofs of quantum advantage. So which means that we've now got quantum computing devices that can run computations in a sort of somewhat broad sense that, would take hundreds of years to simulate on a supercomputer, on a classical supercomputer. Although with the slight caveat that these tasks that prove the quantum advantage, they're very custom built to do exactly this thing of proving a quantum advantage. So they're not kind of questions that are of independent interest. It's basically just you kind of, you come up with effectively a sort of random computation on your quantum computer. And yeah, you know that that's something that would be very difficult to get a classical computer to simulate. But yeah, hopefully in a few years we'll have quantum computers that are big enough that they can actually do sort of computations that are of real world interest as well. So yeah, that was an overview of the motivation of this talk. And so for an outline of the rest of the talk, I'm first going to give you a quick primer on some of the theory of computer science that is relevant, because as I've already mentioned, quantum computing is really at the intersection of these two fields. And so I'll talk a little bit about computer science. Then I'll talk about how we get from quantum mechanics to quantum computers and tell you a little bit about what people are thinking about in quantum computing at the moment and where we've got up to. And then the third section, the ZX calculus, this is really about my own personal research. And I'll try and keep that reasonably short. And then we've got the conclusions. So yeah, let's start with the theory of computation. So, well, when we think about computing things in our computers, in our phones that we already have, everything is based on bits, right? So everything is encoded in just zeros and ones. And so it's enough to just think about functions that go from zeros and ones to zeros and ones. But there are a number of different ways in which we can do that. So in general, kind of writing down an arbitrary function that we want to calculate, that isn't going to tell us how we can actually do that calculation on a physical device, or even how like a human being could potentially do that computation. Instead, we need to break down these complicated functions into sequences of more basic algorithm operations that we know how to implement, whether that's writing commands in a programming language or at a much lower level, machine code, or other kind of more abstract ways of expressing computations. And more abstractly, we can think about different models of computation that tell us basically how a computing device works and what the basic operations are that we've got available to us. And so a standard model of computation is, for example, the RAM model, so random access memory. That's the one it's still sort of somewhat abstract, but it's closest to the way that kind of a standard computer works. So we've got this block of memory where we can just access the memory wherever we want at any time. And that gives us a certain way of organizing our computations and a certain set of basic operations that we want to do on them. But there's also even more abstract and older models of computation that predate any actual computing devices. So for example, the Turing machine, where instead of having a memory where we can just kind of access it wherever we want, instead we've got one infinitely long tape, which is divided into cells. And so each of those cells can have kind of, one, potentially a bit of information, potentially also some finite fixed amount of information that we can store in each cell. And so we can't access these cells at random. Instead, our machine kind of moves backwards and forwards along this tape, and it can only kind of move one cell at a time. And so that makes for a somewhat different model of computation, because now we need to keep in mind in what order our data is on our storage medium, this tape. And then there's also another model of computation called logic circuits. So you might have come across this idea of AND gates and OR gates, these kind of basic logic operations that take 2 bits and combine them into one other bit. And this is also a model of computation that we can think about, and which allows us to talk about things like which computation is more efficient than another one. In terms of by looking at the basic operations of our model and talking about how many of these basic operations are we actually using to compute the thing we're interested in. And indeed, computational complexity is a really important topic in theoretical computer science. So we're talking about the relationship between the size of the input to our problem and the resources that we need to do the computation. And so, for example, for the factoring problem, we're given a composite number which is stored in n bits. So n is the size of our input. And then the task is to find a non-trivial factor of this number. And the question is, well, how many operations do we need to do that, depending on the size of the input? Because, of course, in general, if the input is shorter, then the problem is probably going to be simpler. And so we need fewer operations. But the scaling between the input size and the number of resources that we need, that's the thing that we're interested in complexity. And yeah, so I've talked a little bit about number of operations here, but we could actually look at other resources as well. So for example, the amount of memory that is used, the amount of energy that the computation uses, the amount of time, which is often linked to the number of operations. But sometimes we could have different operations that take different amounts of time, and we could take that into account. Yep. So one really big thing in computational complexity is the difference between polynomial complexity and non-polynomial. One reason that sort of theoreticians like this distinction is because it's actually independent of the model, as long as we stay within classical computer science. So quantum computers, as far as we can tell, break this property. But for classical computers, it's independent of the model, and that makes life a lot easier because we don't need to worry about kind of, did this other person who proved some result work in the exact same model as me? And yeah, so broadly, people think of polynomial complexity as the computations that are efficient that we can do, and non-polynomial complexity, so larger than polynomial, potentially exponential or even worse. Those are the computations that are not efficient to do. And this is also the distinction that people usually use when they talk about whether a quantum computer can do certain things more efficiently than a classical computer. So we'll get back to this notion of polynomial complexity later in the talk. But just kind of to mention that, of course, this is an abstraction. It's very nice in theory, but in practice, it's not necessarily always as relevant as theoreticians like to think. So we've got some algorithms that we know don't have polynomial complexity. They have a worse complexity than polynomial, but actually in many practical cases, they work very well and give us results very quickly. And so, that's kind of one way in which this distinction maybe doesn't hold as much as people like to think. And we've also got some algorithms that on paper have a polynomial complexity, but they're not really practical because, for example, we've got a really large exponent to our polynomial. And so actually, the amount of resources needed grows very quickly, even though it's still a polynomial. And yeah, so nevertheless, for the purposes of this talk, I'm going to think about polynomial complexity versus non-polynomial complexity as being the sort of distinction between things we can do on a computer and things that aren't really feasible. So another kind of couple of things that are interesting from a computer science perspective and will become very important when we think of quantum computers is the topic of optimization. So suppose someone gives you a program that they've written, then, well, maybe there's a more efficient program that performs exactly the same task. So this is, and in the area of optimization, what we're doing is we're trying to find these more efficient programs that do the same thing as the program that we started with. So program here, I'm kind of thinking of quite abstractly. So it could be any sequence of basic operations for our computational model, or it could also be something higher level, like actual programming code in Python or whatever. And again, there's obviously different ways of saying what's kind of more efficient. So we could think about, the number of lines of code. We could think about, the number of operations that it's going to do. We could think about potentially like different operations having different costs associated with them. And therefore, there are some operations that we want to minimize, even at the cost of potentially introducing more of others. So that's what we do in optimization. And on a classical computer, when you actually program something, a lot of this is already built into, for example, your compiler. It will automatically make a lot of really good optimizations. But of course, there's also a lot that we know in general about how to code things efficiently for classical computers. In the quantum world, as I'll talk about in a little bit, we kind of need to basically rebuild all of this knowledge from scratch because very little of it transfers from a classical computer to a quantum one. And as mentioned on the slide, so usually we can't kind of hope to actually get the best representation of our computation, because that again would be computationally infeasible. But certainly we can make some improvements in a sensible amount of time or resources. And then compilation again, so that's kind of broadly translating some high-level description of a computation such as source code in Python into a low-level description such as machine code, or even something more basic for a quantum computation that can be executed on the hardware that you've got. And so this will often include some optimization steps, but also, for example, adapting the instructions that you've used in your high-level description to the specific basic operations that are available on your hardware. And that's something that's particularly important in the quantum world because while all of our processors in classical computers, they're all built in very similar ways. There might be small differences, but they all have the same basic principles behind them. But in the quantum world, we haven't actually settled on how we're going to represent our quantum computations, what the physical system is that is going to do the computation for us. And so different physical approaches to quantum computers have very different properties, very different basic operations that we can do on them, different timescales for those different operations. And as I'll talk about later, also different errors associated with different operations. And so these are all things that we want to take into account when we do computations. So so that was the end of my primer on theory of computation. Are there any questions before I move on to the next topic? Okay, so now let's talk about actual quantum computers. So one of the nice things about working in quantum computing, having taken previously a sort of standard introduction to quantum mechanics course, is that a lot of the things that are difficult in quantum mechanics we can just ignore when we work in quantum computing. So the states of our quantum systems that we work with in general in quantum mechanics, we spend a lot of time working with infinite dimensional systems. So there's a lot of calculus involved. In the quantum world, in the quantum computing world, our states are usually finite dimensional. In fact, we most often work with qubits, which are quantum bits. So they're two-dimensional systems. I'll go into that in a bit more detail in a moment. And also, at least on the more sort of computer sciencey side of quantum computing where I'm based, we usually work with pure states. So actually we can do everything just in terms of linear algebra. Our states are vectors. Again, that makes life a lot easier than kind of the sort of work that I did in my first quantum computing courses when I took them. Then for the time evolution, in general, in the quantum world, our systems develop according to some Hamiltonian. But in quantum computing, we usually assume, at least to a sort of first approximation, that our systems are closed, and so our evolution is unitary. And again, that means that we can use linear algebra to represent our transformations. In terms of measurements, so in the quantum world, if we want to read out information, gain information about our system, we have to measure it. And again, we can often kind of restrict ourselves to just the simplest case of measurement, which in this case is Hermitian observables, or even just one specific Hermitian observable that people sometimes use. I'll get onto that on the next slide. And then in terms of composite systems, we usually assume that our systems are distinguishable. So in fact, if we use the word qubit, quantum bit, that implies that our different qubits are all distinguishable, for example, because they're each at a well-known location in space. And so we don't need to worry about effects of bosonic or fermionic statistics. Although some people do also specifically consider computation on bosons or fermions and the effects that that has on the computation. There are some ways that one can exploit that. But I will just talk about qubits in this talk, so about distinguishable systems. So that means that we've got these quantum bits with a two-dimensional state space. And then if we've got n qubits, that just means that our state space has dimension 2 to the power of n. And we can write that, as I've already mentioned, just as a state vector for our system.
Sorry, Miriam, may I interrupt?
Yeah, sure.
What did you mean about the pure states? Is that you mean that it's not a composite state? It's
so pure states as opposed to mixed states. Pure states basically are the state vectors. And then if we want to use mixed states, those would be probabilistic mixtures of pure states. But we don't use those so much, at least in my area of quantum computing.
Thank you.
So yeah, generally we've kind of got a single state that we know, a single state vector. Yeah. Okay, so yeah, to look a little bit more at these qubits that I've mentioned. So we usually choose an orthonormal basis for our qubits that we call the computational basis. And so the two states of that basis we call the state ket0 and the state ket1. And so every state of a qubit can be represented as a superposition, a linear combination of these two states. I'm going to lose, I don't think I'd actually write down that many states in this talk, but just to note that, yeah, in general, sort of strictly speaking, when we write a state of multiple systems, we should put tensor product symbols in between the different states. So here we've got, yeah, a state on kind of 5 qubits. The first one is ket0, the second one is ket0, third one's ket1, and so on. But where there's no space for confusion, we often drop the tensor product symbols, or we even just write everything in just a single vector, a single ket, just to keep things simple. And yeah, as we said, our computation, our transformations on our qubits, they're all unitary transformations. So in particular, that means that our transformations need to be invertible. And so that gives us a little bit of a tricky situation when we want to do computation on qubits where we've previously got an algorithm or like a way of doing it on a classical computer, because our classical computations are not generally invertible. But there's a trick that we can use to make any classical computation into something that's invertible so that we can, in principle, implement on a quantum computer. And that is that rather than just having kind of our input and system and some output system, we actually put the two systems next to each other. So we have kind of one input system. So this could be n qubits. And oops, sorry, there's a mouse somewhere in the way. No, it's not my mouse. That's weird. Okay, so yeah, so we've got our input system, and in parallel to that, we have another system which is going to hold the result of our computation. But we just put them both next to each other. And then we implement our computation in such a way that we add the result of the computation to the state of the second system. So we can think of this all as being encoded in binary numbers. And so we just use kind of the addition of these binary numbers over here to add the result of our function to whatever value was already there. And so this is now an invertible transformation, because if we kind of, instead of a plus here, if we set it up with a minus, then we can undo the transformation that we just did.
You mean this one is addition?
So this plus here, this represents addition of binary numbers. So we think of our...
This one is for actual addition of binary numbers.
Pardon?
This one.
Bitwise. No, I mean, it could be, or it could also be standard addition modulo 2 to the m, depending on, yeah, like what your result is. But I guess, yeah, if you've got multiple qubits, then you would usually use just standard addition modulo 2 to the m to get your outcome onto this output register. Yeah, sorry, I didn't hear you well at the beginning.
Sorry, Miriam, may I interrupt?
Yeah.
Did you say the classical computers are not invertible?
So they're not invertible in the sense that if you just get the output of a computation, you can't necessarily tell what the input was. So, for example, yeah, like a classical, like if you think of addition of two numbers, right? If you tell me 1 plus 2, I can tell you 3. But if I tell you 3, you don't know whether that was 1 plus 2 or 0 plus 3, or I guess potentially if we allow negative numbers, there's even more options. So you can't necessarily go from the output back to the inputs.
And quantum computers do have.
You need the operation that you've done in any case.
No, but you're given the operation, you can't go back.
Yeah, so given the output, you can't necessarily recover the inputs of an operation.
Even if you know what gate happens.
Yeah, even if you know what operation it is. So like, yeah, I tell, like if you tell me I've added 2 numbers and the result is 15, then yeah, like I can't know which numbers you've added. And yeah, so here, in order to avoid this, we kind of keep the inputs alongside that output, and so that then means that yeah, we can undo our operations and we can recover exactly the state that it was in at the beginning before we did the transformation.
So if I define addition on a quantum computer and I tell you the result was 15, it could actually tell me what the input was?
Sorry, there were multiple people speaking, so I couldn't quite hear you online.
I said, so on a quantum computer, this is invertible. So if I gave it 15 and addition, it would know what numbers I've added.
No, I mean, if you just give it 15 and addition, it wouldn't know. But the point is that if you want to use a quantum computer to add 2 numbers, you have to do it in such a way that your output isn't just 15, but it contains extra information that allows you to then undo the addition and recover exactly the initial state.
Got it. Thank you. That's beautiful.
Because yeah, like if the output is just 15, then yeah, then there's no way this could be a unitary linear transformation, because unitary transformations are always invertible.
I don't see the
result from the scalar.
So the distinction between what?
If I give you the unitary transformation,
yeah,
I have to specify the input and the output. There is it's a matrix transformation.
Yeah, yeah.
But I have to keep that amounts to giving you the same data in the classical case. So
yeah, so I mean, in the classical case, if you want to do like
if
addition,
I don't give you if I just tell you it's unitary, like I told you it's plus, you won't be able to tell me that what the answer was, what it came from. I got this vector here by a unitary transformation.
Yeah, no, I mean you do.
It's the same problem.
You need to know, like, yeah, just giving the output result isn't enough. Like, if I wanted to invert it, I would also need to know what the unitary transformation was exactly,
So
like
there's
the
a
actual
distinction.
matrix. Yes, there is, because in the classical world, you don't do your operations with unitary transformations, right? And so, yeah, like in the classical world, you can give someone like a program or some kind of lower level specification for a computation, and an output of that computation, and the other person won't be able to recover the inputs from that. Whereas in the quantum world, if you give me the specification of a computation, so you give me a unitary operation and you give me the output state, then I can calculate what the input state was. because the unitary matrix is invertible. I mean, it might not be efficient to invert it because, yeah, in general, if it's a large unitary, that's...
It seems to me not artificial distinction. You're leaving something out there. And we can move on. It's not
yeah, I don't think I'm leaving anything out, but yeah, like clearly there's some kind of communication issue here. Okay, so yeah, so we can, I guess the point here is that we need to do a little bit of work, but we can embed all sort of anything we can calculate on a classical computer, we can also calculate on a quantum.
So you're saying that a Turing machine is not invertible?
Yes.
In that sense?
Yes.
Yeah.
It's make one, always return one first if it was.
Exactly, for example. And that's a valid Turing machine, but yeah, in the quantum world, it's not allowed.
You erase information when you're doing your computation.
Yeah.
Unless you keep it all, like, but that's exactly what you're doing there.
Yes.
If you remember everything that you had before, but that is called a huge waste.
Yeah, so you can also do reversible computation classically, in sort of, yeah, roughly this form. And in fact, there is, I think, a little bit of research in that direction because erasing information is what costs energy. And so there is this idea that if we had a classical reversible computer, potentially that could be more energy efficient than the standard computers we're using. But clearly it's not kind of really caught on because we're using, yeah, computers that aren't reversible.
Sorry, I have another question. So that means it is not just the initial states that are pure, but also your final states have to be pure. Is that right?
Yeah.
Good. Okay, thank you.
So again, there are also some people that do look at mixed states, but yeah, like for what I'm looking at, as I mentioned, I'm sort of more on the computer sciencey side of quantum computing these days. And so there, I just look at pure states, unitary evolutions, so everything remains pure.
Thank you.
Cool. Okay, so let's move on. So yeah, so as I've just explained, we can do any classical computation on a quantum computer, but in practice, we shouldn't and we wouldn't want to. I'm going to talk a little bit more about this on the future slides. But so one point is that actually our quantum computer, it's always going to work together with a classical computer that drives it, that sends it the instructions and so on. And so it doesn't really make sense to do things on the quantum hardware that we can also do efficiently on our classical computer. So yeah, it's probably better to think of a quantum computer as a quantum coprocessor, so something like a graphics card in a computer that is very good at certain kinds of computation, but yeah, it's not going to just completely replace the processors that we normally use. Okay, so the reason I talked to you about models of computation earlier and about logic circuits is because in the quantum world, so it is possible to define a quantum Turing machine, but it gets a little bit strange once you've got kind of a superposition of your Turing machine being in like two very far apart locations on your tape. And so instead of working with quantum Turing machines, people usually work with quantum circuits as kind of the really low-level specification of our quantum computation. So these are a generalization of the reversible version of logic circuits. And so the way we can think about these is having sort of, think about the whole model of computation, that is the quantum circuit model, is that we've got three types of operations that we use when we do computation. So we can prepare states in our computational basis. So that's something very, very simple, independent of the computation we're doing, really. Then the main part of our computation is what's called unitary gates. So I'll talk a little bit more about what makes a unitary gate in a moment. So here's a few examples of sort of single qubit gates that are going to appear in my example circuit that I'm going to show you in a moment. And then we can use measurements just in the computational basis at the end to read out the information, the result of our computation. So here's an example of one of these circuits. So we've got all these these three wires that are kind of horizontal through the circuit. These are 3 qubits. And then each of these boxes with a letter is one of our single qubit gates. And then these lines that are connecting to 2 wires, these are 2 qubit gates. In this specific case, they're controlled NOT gates. So they're actually a classical reversible gate that we could also use if we're doing computation on bits. But of course, these other unitary gates here, this T, this S, this H, these are intrinsically quantum. We couldn't do them on bits. because they either add a phase that is meaningless if we work with bits, or they create a superposition of our computational basis states, which again isn't something we can have when we work with bits. And so these quantum circuits are how we usually specify quantum computations. And then we can, for example, use the number of gates in our circuit or the number of layers in the circuit as a measure of computational complexity. There's one slight caveat that I should mention, which is that our circuits have to be uniform if we want to really use them to figure out which computations are efficient to do on a quantum computer. So uniform means that there should be some kind of straightforward way of, given the input size, figuring out what the circuit is that implements our computation that we want to do. Just to avoid kind of edge cases of people encoding really difficult to do computations in the definition of the circuit. But that's really a sort of kind of aside that isn't so important for the overarching picture. So these quantum circuits, the choice of the gates that we use, that's really determined on the one side by the hardware that we want to run our computation on, but also by theoretical considerations like what's easy to work with, for example. So one nice thing about quantum circuits is that these 1 and 2 qubit gates are actually enough to be working with. Whereas if you want to do classical reversible circuits, we know that we always need a 3-bit gate as well to just be able to implement any computation. But in the quantum world, the sort of, like just the 2 qubits and the 1 qubit gates, those are enough.
So what did you say the full dots and the empty circles were?
Pardon, what are the...
the full circles and the empty circles.
Right, thanks. I didn't actually say that. Yes, so these controlled NOT gates, they're not symmetric in the 2 qubits that they act on. So the idea is that where there's the full dot, that's the so-called control qubit. And then the hollow dot, that's the target qubit. And what it does is it flips the computational basis state of the target qubit if and only if the control qubit is in the state 1. So that's why it's called kind of a controlled operation. So it's controlled on the state of the first qubit, the control qubit, and then it applies this flip operation, this NOT operation to the second qubit.
Oh, thank you.
And so we can apply them in kind of whatever direction we want, at least in theory. But again, in practice, in our hardware, we might have restrictions on which 2 qubit gates we can apply. So for example, in certain kinds of quantum computing architectures, our qubits, as I've mentioned, they're in specific places. And so we might only have kind of specific sort of nearest neighbor 2 qubit gates, controlled NOT gates that we can apply. We can't just kind of do them between arbitrary qubits that might be very far apart from each other. And we might also actually only be able to do them in one direction. But that's also not a problem because we can actually flip the direction of a controlled NOT gate by just sandwiching it between these Hadamard gates of all the qubits. So that's not kind of a straightforward thing to see. I don't expect you to kind of know why this is true, but this is sort of a question that we usually set to the students when they start working with quantum circuits to work out why if you take a controlled NOT gate and you put Hadamard gates on all the input wires, all the output wires, then what you actually get is a controlled NOT gate, but with control and target reversed. So that's kind of a really weird thing, again, sort of coming from classical computing. Why would you be able to reverse the control and the target of an operation just by doing local things on the individual wires? So as I've mentioned, kind of hardware considerations are also important when we think about which gates we want to use. And in fact, while in theory sort of 1 and 2 qubit gates are enough, in practice, at least for some quantum computing platforms, we do also have access to global gates that can act on either all the qubits at the same time or on some chosen subset of the qubits. So for example, in ion traps, there's the Milner-Sørensen interaction that does this sort of transformation. But again, this is something that is very specific to the kind of quantum computing approach that you want to work with. And I guess maybe just in case it wasn't entirely clear, so we've got our qubit wires here, and sort of the horizontal dimension is basically a sort of notion of time, right? So we do this layer of gates on the left first, and then we do the next layer of gates, and so on, all the way through. Okay, So now why are people so interested in quantum computing? What are the advantages? So in the quantum world, our n qubits can actually, in principle, store 2 to the n complex numbers as the amplitudes of the state vector. I mean, our quantum state vectors, they always have to be normalized, so kind of we can only store them up to normalization. But that still gives us quite a lot of space to work with. And it's really powerful, like, being able to store these 2 to the n numbers in just n objects, because then we can manipulate them using a much smaller number of operations than we'd otherwise need. But of course, it's not quite as simple as that. For some arbitrarily chosen set of 2 to the n numbers, we're not going to be able to prepare the state that has these 2 to the n numbers as its amplitudes in any efficient way. So even if we wanted to, we can't kind of use this sort of like property of just being able to store our data in a really concise way for arbitrary data that we start with. So instead, it has to be something where we can prepare our quantum state that has these 2 to the n amplitudes in an efficient way. And that works often, but it doesn't work always. And so that's something to keep in mind. And then also, we can't actually read a lot of information out of a quantum state. So if we do a measurement on a single qubit, that measurement effectively gives us 1 bit of information. So when we do a measurement using the observable that corresponds to the computational basis, we'll get a result 0 or 1. And we don't actually learn anything in detail about the actual complex amplitudes of our original state. And there's no way we can get around that, because quantum states, unknown quantum states, cannot be copied. So I can't kind of take an unknown state, make many copies of it, measure them all, and then kind of work out detailed statistics. That's not going to work, because there's no general process that copies quantum data. And so, in practice, we're stuck with this fact that while we can have a huge amount of information stored in our quantum state, but we can't read it out. And so a lot of what people do when they kind of come up with algorithms for quantum computers is actually figure out ways of manipulating the information so that at the end we can measure, and the outcome of our measurement will be exactly the information that we're interested in and nothing else, so that we can kind of get the most use out of the computation that we've done.
Sorry, Miriam, again. So this doesn't go against what you said before, that removing information also costs energy.
No, this doesn't go against that removal of information. I guess quantum measurements probably do cost energy in general.
Mm-hmm. But you're not removing any information, right? You've defined your input state.
No, I guess in a sense you probably are removing information during the measurement.
Mm-hmm.
But see it into particular states. So
exactly. So you're collapsing the state, and so there must be information that is lost in that process. But this is why the measurement is kind of separate from the unitary evolution.
Mm-hmm. Mm-hmm.
Unitary evolution, that's the part that doesn't lose any information, but then the measurement does.
Mm-hmm. Thank you.
it's a projection.
I mean, projective measurements are like one approach to measurements. There's some slightly more general definition one can make for measurements in quantum mechanics, but thinking about it, a projection is a good approach. So as I've mentioned, kind of in principle, reversible computation could be more energy efficient. But on the quantum side, we've got these measurements that are not reversible. Also, when we work in quantum computing, a lot of quantum hardware actually needs to be cooled down to near absolute zero. So again, obviously, that's not terribly energy efficient in general. Another kind of big caveat to keep in mind about quantum computing is the fact that, in a sense, quantum computing is both discrete and analog. So we have our discrete computational basis states, the 0 and ket1, but our state vectors are described by continuously varying parameters. And so that means that together with the fact that, of course, systems that exhibit quantum effects tend to be very small, that means that errors are unavoidable. We can't completely isolate our quantum system that we use to do computation because we need to control it to actually drive the computation. But then, yeah, there will be interaction with an environment. And so, yeah, all the things that I've said so far about working with pure states, it's a nice abstraction. It works well when we're thinking about the sort of computer science side of things. But in practice, at some point, we need to take into account that this is not a closed system. And so things are much more complicated than, yeah, one would like to think.
Sorry,
And so,
again, if I may. So why does the quantum computing hardware have to be close to zero? Is it you will introduce impurities into the initial state, or?
Yeah, I mean, in order to really see sort of like pure quantum states, like if you were, for example, have an ion as your qubit, yeah, that just needs to be at a very low temperature. Otherwise, it's going to be in a superposition of many different states. In particular, yeah, because many of the systems we want to use as qubits are actually not two-dimensional intrinsically. It's just we want to use their two lowest energy states to be our qubit, and so we want to minimize the risk of it going into a higher energy state. And sort of, yeah, going out of the state space of the qubit. So that's one reason. I guess one system that is intrinsically two-level is something like the polarization of a photon. But then, of course, if we want to generate photons and if we want to measure photons, that again are things that I think, yeah, certainly the photon counters, I think they do need to be cooled quite a lot to to really give us single photon counts. Yeah.
Thank you.
Thanks for the question. Yeah, so that all means that really, quantum computation, there are a lot of questions to be resolved if we want to make it work. So one thing that, I wanted to go through at least like one of the approaches, like one of the algorithms for quantum computing in, again, like at a very high level to explain to you kind of like one of the things that people expect to do with a quantum computer. So actually, I think my favorite application of quantum computers isn't so much, Shor's factoring algorithm as it is quantum simulation. So yeah, the ability to simulate other quantum systems efficiently, which I think is, has like just a much wider range of applications in the real world, and also is something that might be feasible in the nearer term because it doesn't necessarily require kind of digital computation to do, but we can use computations that are much more approximate. We can run them multiple times to kind of get results about some sort of energy of some quantum system. So it doesn't need to be kind of exact and digital, and that means that it's probably going to be practically possible much sooner than something like this factoring algorithm. But on the other hand, I think the factoring algorithm really shows more of like the power of quantum computation really sort of intrinsically. So let's talk about that a little bit. So the factoring problem is the problem of given a large number and the promise that this number is composite. So it's a product of some non-trivial numbers, and the task is to find one of these factors. So non-trivial in the sense of it's not 1 or n itself. Those are the trivial factors. And well, classically, we don't know an efficient algorithm for this, despite a lot of searching. We don't actually have a proof that it's not efficient, but people are sure enough that, it's going to be very difficult to find an efficient algorithm, if it's at all possible, that it's actually at the basis of the RSA public key cryptography scheme. So the idea is that, kind of your secret key that you keep to yourself is kind of two factors, and then you multiply them together, and that product is the number that you can publish. You can hand it to anyone, and they can use that composite number to encrypt things, and then only the person who has the two factors can decrypt. So that's really useful because you don't have to keep your public key secret. In many other cryptography schemes, the keys need to be secret, and that makes them very difficult to share between different people. I have to have different secret keys with each of you if we want to be able to exchange messages. But for a public key cryptography scheme, I can create one public key that I give to all of you, and then all of you can encrypt messages to me. And yeah, each of you just needs to make one public key, and then I can send secret messages to you. So rather than we just need n keys in total for n people, whereas with the secret key system, we'd need kind of one key for each pair of people, right? So n squared in general. Okay, so that's that's why factoring is really important. And yeah, one of the early examples of an algorithm that a quantum algorithm that is really better than any known classical algorithm is Peter Shor's algorithm for factoring on a quantum computer. And so this algorithm is kind of interesting because it doesn't actually solve factoring directly. Instead, there's a lot of sort of mathematical work in the background that turns the factoring problem into a problem of period finding. So there is a way in which one can turn the problem of finding the factors of a number into the problem of you can kind of use that big composite number to set up some function, and you're guaranteed this function is going to be periodic, it'll repeat, and that period, the length, will tell you about the factor of your number. So it's I don't want to go into the mathematics of how to do that, it does get a bit complicated, but the point is that we can set up this function that's going to be periodic quite easily on both a classical or a quantum computer. And so we can encode this sort of periodic data into a quantum state. So that we can do efficiently, we know that. And then what we can do is we can apply a discrete Fourier transform to this data set to find out about the period. And the point is, because we can encode 2 to the n values into our n qubit state, we can then actually do a Fourier transform on these 2 to the n values using just a number of operations that's polynomial in n. Whereas if we were trying to do it on a classical computer, because there's 2 to the n data points, we at least have to touch each of these data points once, otherwise we can't do anything with them. And so the number of operations that we need to do on a classical computer cannot be polynomial, it has to be exponential. And so that's the big difference between doing a Fourier transform on a quantum computer and on a classical computer. And so that's why really this factoring, this period finding approach can't give us an advantage on a classical computer. It doesn't give us a polynomial time algorithm for factoring on a normal computer, but it does on a quantum computer.
Sorry, may I jump in with a question? So in machine learning, there's something we do called principal component analysis. And we kind of do a similar thing that, you encode 2 pieces of information in one element, similar to the, I guess, cryptography scheme.
Yeah.
Is it accidental, this similarity?
I don't know much about this principal component analysis, so I don't know, but I guess, I mean, the idea of encoding multiple pieces of data into one thing, I think, is not rare. What's really interesting about this kind of composite number and the factors is that like we've got this, it's very easy to multiply 2 numbers together, but given the product, it's very difficult to find the individual factors of it. Or at least, no one has found a good way of doing it on a normal computer yet.
Towards the end of your talk, I will ask you about quantum machine learning. But let's see if we get there.
Let's see. Thank you. So the other thing I wanted to say about this factoring, actually, one of the advantages of it is, so it's a discrete algorithm, so it really wants to work with bit values. But it can also tolerate a reasonably high probability of error because we have a straightforward way of checking answers, right? Like if the algorithm spits out some number A, I can see whether A divides n without remainder, and that's something that, again, I can do efficiently. And if there is a remainder, like a non-zero one, I know it wasn't actually a factor, there was an error. And if it does divide it, then I can be sure that I have found a factor. And so that means that our algorithm can be probabilistic, and indeed this factoring algorithm on a quantum computer is probabilistic. So it doesn't always give us the same result, and it doesn't always give us the correct result. But we can show that it gives the correct result with a high enough probability that if we repeat it a few times independently, yeah, at some point we have a very high probability of having seen the right answer. And yeah, because we can check answers, yeah, we can just after each run, we check, was this a correct answer? And if no, we run it again. And if yes, we know that we can stop. Okay. So yeah, as I've kind of mentioned down here, so we can check answers for this specific algorithm, but of course there might also be things that we want to do on a quantum computer where we can't check answers, and so we really yeah, can't tolerate a very large probability of error. And as I've mentioned earlier, in fact, in the quantum world, we have to take into account the fact that there are going to be errors in our computation, because our quantum systems are very small. We can't isolate them perfectly from the environment. So the states are going to change over time in ways that are not intentional by us. Yeah, as I've already mentioned, we can't actually copy unknown quantum states. So that's kind of, yeah, potentially removes one of the sort of most obvious ways in which we can protect data. In the classical world, within a single computer, we don't need to use error correction because errors are so rare, we just, yeah, don't worry about them. But if I send information over the internet, for example, then yes, I can just send it multiple times, right? And the other person can, yeah, either take a majority vote, or they can use some kind of other way of checking the integrity of the data they've received to know whether it's correct or not. But that doesn't work in the quantum world. And then also, again, in the classical world, in order to kind of compare the multiple messages I've received, for example, to take a majority vote, I need to actually be able to look at each of them. But in the quantum world, when we make a measurement, we change the quantum state. So again, this is something that kind of makes quantum error correction quite a challenge. But it turns out we can actually get around these challenges. Yeah, we do believe that we're going to be able to implement error correction on a quantum computer so that we can do large-scale computations and keep the errors, yeah, as small as we want them to be. And the idea here is that even though we can't copy unknown quantum states, we can kind of do other ways of sort of spreading our information across a larger quantum system. So for example, we might start with 1 qubit and yeah, not exactly copy it, but yeah, sort of use a unitary, well, I guess unitary operation isn't quite the right word here because it's not going to be unitary necessarily, but yeah, some embedding to kind of put our quantum state into a larger system. And we can do that in such a way that there are specific measurements where we know those are not going to change our valid code word, so a state that arises from encoding some initial state that we want to make resistant to errors. And so, yeah, we're not going to kind of measure all the information there is to measure, but we're just going to measure certain correlations between different qubits in such a way that we don't change our code words. But do get information about if there was an error. So one example here is maybe, this is a simple like toy example that doesn't kind of correct all the errors there could be. But what we can do is we can set up a setting where we encode our computational basis state ket0 into just 3 copies of ket0, and we encode ket1 into 3 copies of ket1. And so this doesn't break what I've just told you. This doesn't contradict the fact that we can't copy unknown quantum states, because what we're copying here is just the 2 known states. And in fact, other quantum states, so if we have a state that's, say, A0 plus B1, then that one isn't going to be copied. That one will instead become, by linearity, A times 0, 0, 0 plus B times 1, 1, 1. So this is kind of the most general form of our encoded state. And then what we can do here is we can measure the parity of the first 2 qubits. So we can check whether they're in the same computational basis state. And of course, in our valid code word, they are in the same computational basis state, right? They're either both 0 or both 1. And so this measurement doesn't change our valid code word. And we can also do the same thing to the last 2 qubits. So we can check are the last 2 qubits the same. And again, that's something that doesn't change our code word state. But if we had a bit flip error on one of the qubits, so if in one place a 0 became 1 and a 1 became 0, then that's something that we can pick up on by doing these parity checks. So for example, if we end up with a state that's something like alpha 1, 0, 0 plus b, A plus b 0, 1, 1, then if we check the parity of the first two qubits, we'll now get a different result, because now they're no longer equal to each other. And so in this way, we can find out that one of these bit flip errors happened. And then we can find a way to correct it. And this all happens without destroying the superposition that we're really interested in, which is the superposition between these two states.
Sorry, the parity flip is due to the measurement, or due to the?
No, so this would be if an error has happened. So that flip here, this would be something that we don't intend, right? But like an interaction with the environment, for example, happens to affect this first qubit and flip it from 0 to 1 and from 1 to 0. And then our parity measurements will pick up on the fact that now this parity is different. Right? Yes. So the second parity will still be the same, so we'll still have 2 zeros, 2 1s, but the first parity will be 1 0 and 0 1, so this will give us a different measurement outcome.
And what would have caused that would be a hardware problem? The temperature went up, so
so not necessarily like a hardware problem as such, but yeah, as I mentioned, like we can't perfectly isolate our quantum systems from the environment, so we just have to know that errors are going to happen. There's no way to avoid that. So it's pardon?
It could be a terrible fluctuation.
Yeah, so some fluctuation, exactly, thermal or whatever.
Okay, now may I also ask a naive question? Do you have the distinction of a perturbative versus non-perturbative calculation in quantum computing?
It's not something I'm personally familiar with, so there might be other people who use that, but yeah, it's not something that I've come across.
So you don't know if the leading or the result of the calculation is always bigger than the next leading order?
So that's not an approach that I'm familiar with. Sorry.
Thank you. Yeah, no, that's good. I'm not even sure it is a question that you would ask.
Then we would not be able to decode correctly, right? Then we would, when we try to apply a correction, we would end up in a different state to the one we started with. So I mean, that's always the problem with error correction, right? Like in trying to correct errors, you actually make your computation more complicated. You add more qubits, so that to some degree that increases the probability of errors happening, but it also gives you the ability to notice and correct some errors. And so there's this concept of a threshold in error correction, which means that if the initial error probability is too high, then your attempt to help is actually going to make things worse. But if the initial error probability is small enough, then the probability of having more errors happening at the same time is sufficiently small that you end up correcting more errors than you introduce by adding the extra qubits, which have the capability of having errors on them. So one other thing, so like the error that I talked about here, this bit flip error, this is quite a big change, right? It's not something that kind of makes a really small shift to our state. It really it goes from one state to an orthogonal state. That's quite a big thing. But it turns out that's actually okay, because here, the way that our measurements change the state actually helps us. So if I've got an error that is some kind of general unitary operation, which we can think of as being partly an identity and partly this bit flip, then our measurement will either send us to the situation where everything is fine, no error has happened, or it will send us to the scenario where the full bit flip happened. So our measurements take us from these potentially small continuous errors to just a set of discrete errors, which are then kind of much easier to correct and to recognize. This is due to the fact that if you've got any kind of single qubit unitary matrix, you can always write this as a superposition of the Pauli matrices and the identity. Let's see whether I can work this out on the fly. So we're going to have a plus d by 2, I think, times the identity matrix. And we're going to have a minus d over 2 times the Pauli Z matrix. And then, yeah, I won't work out the others, but we've got our Pauli X and our Pauli Y. I keep forgetting where the i's go, but yeah. So we can write each matrix as a superposition of these 4 Pauli matrices, and then yeah, when we make our measurement, it will pick up exactly one of these Paulis, and kind of everything else will be collapsed. And so we're just in the situation where our error has the form of either the identity, so no error happens, or one of the Pauli matrices. And so that's where, yeah, as I said, the fact that measurements change the state actually helps us, because they take us from this kind of really general error to the scenario where just a specific error happened.
Wait, so this error correction, that assumes that you expect what the result is going to be. What if I've never done a calculation that is actually going to flip one of my states?
You don't need to know the answer of your calculation. What you just need to know is like the way that you've encoded your initial data into some larger system, and yeah, basically the types of measurements that you expect, like what to expect. You leave your encoded state invariant, and what outcomes you expect if you're in a valid encoded state. And then if you're not in a valid encoded state, you would expect different results of your measurements. And this is all independent of which exact state this is. So we don't need to know the values of A and B here in order to do this correction.
Okay, got it. Thank you.
Yeah, thanks. Yeah, so that means that, yeah, quantum error correction is possible. As I've mentioned, there is this question of the threshold. So we do need to first, as a challenge to the experimentalists and engineers, the errors on the physical system need to be small enough that our error correction doesn't introduce more errors than it solves. But then there's also like a lot of further questions that we need to, or that people are actively working on. For example, how we can compute on these encoded states in a fault-tolerant way. Because once we've done this encoding, this isn't all of our job done, right? Where we're not using this encoding just to kind of store data, to leave it sitting there idle by itself, but we actually we need to be able to do computation on this encoded data in a way that isn't going to kind of take one error that's happened somewhere and like spread it to lots of different places. Because if we do kind of get this situation where one error in one location actually sort of turns into errors in many locations, then our assumption that it's unlikely that we have correlated errors, that we have more than one error at the same time, is no longer true, and then our whole error correction process breaks down. So yeah, so this is not my area of expertise, but it's something I've been kind of looking into a little bit more recently, and I think it's really like sort of an important aspect of quantum computing. So that's why I wanted to tell you about this whole area of quantum error correction. Another aspect is actually more of a sort of classical computing challenge. It's like we've got our error correcting code, and in general, I mean, this is a really simple toy example that I've written up on the board here. So in general, we're going to potentially encode multiple initial qubits into some large number of kind of data qubits, and then our measurements are going to be quite complicated, and there will be many of them that we use to try and find these error syndromes. And then it's not always easy to go from this error syndrome to actually figuring out which errors are most likely to have happened, and so what do I need to do to correct and get back to the right state. And if your decoding procedure is too slow, then you have your qubits kind of sitting idle, and during that time they will acquire even more errors, which you then have to decode. And then you end up unable to do any computation, because kind of just the amount of work you need to do to decode and fix your errors just builds up and drowns out everything else. But these are all like issues that are fixable. They're very active, ongoing areas of research. So maybe now taking us back a little bit more into the area of things that I'm working on. As I've mentioned earlier, kind of optimization of quantum computations is something that I'm very interested in. So this is something that's particularly important kind of in the short term, when our quantum computers are very small. The error rates are still very high, And so we can't actually use this active error correction process that I've explained to you on the previous slide. So instead, we need to either tolerate the errors, or we need to use kind of other what's called error mitigation techniques to try and avoid the errors that we have. So yeah, that makes it particularly important that our computations are kind of as short and as simple as possible while achieving the thing that we want to compute. But even in the longer run, yeah, we expect that quantum computers are going to remain sort of limited for some time. And so, yeah, we want to make sure that we use them effectively. And so one approach here is that we can identify parts of a quantum computation that we can also do efficiently on a classical computer. And then, yeah, we just sort of, yeah, figure out how to split the computation so we can kind of do it, yeah, partly on the quantum computer, partly on the classical computer. Another approach is this thing that I talked about earlier with optimization, that we find a more efficient sequence of instructions that implements the same computation as our original one. But again, that's something where, yeah, we can't generally hope to find the best sequence of instructions, but we have some very good heuristics that in many cases do give us better outcomes than the thing we put in at the beginning. But then that actually like throws up a new question, and that is, well, if we've got this computation and we've optimized it, like how can we guarantee that this optimized set of instructions still implements the same operation as the original one? So that is also something that's, yeah, obviously we need to ensure, because errors do sometimes happen on the classical side as well, not in the sense of like hardware faults, but yeah, just in the sense of software problems, for example. And of course, in general, like we don't want to be doing all of this by hand. We really want the computer to be doing it automatically. And for classical computing, we have a lot of really good techniques, really good software already that handles all of this. But in the quantum world, we basically, yeah, can only reuse very limited parts of that because of all these questions, like we can't copy quantum data. Our computations have to be reversible. This means like everything looks very different. We need to take into account error correction and all of that. We have these hardware settings where only specific types of gates can be applied in specific locations. Yeah, and so this is kind of roughly the area that I work in. And yeah. Which can maybe sort of partly be described as working towards a quantum compiler. So that can, yeah, some software that can take in a very high level description of a quantum algorithm, and then, yeah, like do all these optimizations and everything and adaptations to specific hardware, and kind of, yeah, spit out a set of basic instructions that we can run on that hardware. Yeah, so that takes us to the end of my second part, but I realize I'm already over time. Do you want me to go through kind of the description of my own research, or should we like just take some questions and then wrap it up here?
I definitely want to hear about your work.
Okay, so yeah, in that case, I'll continue. So yeah, so what I'm working with is this graphical language for computations on qubits. So the quantum circuits that I've shown you earlier, they're already kind of a graphical language, right? I showed you this diagram of them. But the ZX calculus is a lot more flexible. So that means that, for example, when we want to optimize things, we have a lot more options for how we can do that. At the same time, it is more, I guess, further removed from the things that we can really implement physically. So the basic components of the ZX calculus don't have to be unitary, so we can't necessarily actually implement them directly in practice. If we've used the ZX calculus for optimization, at the end we always need to kind of translate back into something that we can actually implement.
Where does the name come from? Sorry, where does the name come from?
It's like this computational basis. It's also called the Z basis because it's the eigenbasis of the Pauli Z matrix. And then the ZX calculus also uses the eigenbasis of Pauli X. And that's the X.
That's it. Thank you.
So yeah, I'll actually show you in a moment kind of how exactly these two bases come into it. So yeah, so we've got this extra flexibility when reasoning about quantum computations, but at the cost of more effort when we want to translate something into an implementation later. But so far, it really seems like this trade-off is worth it, and we can or we can get kind of state-of-the-art approaches to optimization, for example, using the ZX calculus. Yeah, so what does the ZX calculus consist of? So rather than having quantum gates, we have these objects that can have a lot of wires going in and a lot of wires going out, and they're called spiders because I guess they look a little bit like a spider, even though yeah, so they can have arbitrarily many inputs and arbitrarily many outputs. And then we've got this one slightly more boring one, which is this little box which always has exactly one input wire and one output wire. And so these represent certain maps. So the green spiders, the Z spiders, they represent a map in the computational basis. So we take, we kind of project, yeah, I mean, projection isn't quite the right word because it's not sort of necessarily something with equal numbers of inputs and outputs. But it's sort of a generalized projection maybe, where either we expect all the input qubits to be in state 0 and all the outputs are then also in state 0, or we expect all the inputs to be in state 1 and then all the outputs are also in state 1, but we have this phase that's sort of between the two things. So if you want to write it all as one big matrix, we end up with a 1 in the top left corner and this e to the I alpha in the bottom right corner and zeros just everywhere else. So this is, yeah, like a very broad family of operations. As I said, they're not necessarily directly implementable, but they're really useful from a sort of theoretical perspective. This little yellow box, that's the Hadamard gate, which we've already seen before, just kind of written with an H. So that maps between the computational basis, so the Z eigenbasis, and the X eigenbasis, which is usually called, denoted by plus and minus, so ket plus and ket minus, as defined down here. So it's an equal superposition of ket 0 and ket 1, with either a plus sign or a minus sign between them. And this red spider, this X spider, it does the same thing as the Z spider, but it does it for the X eigenbasis rather than the Z eigenbasis. So I'm not going to write out the matrix because that gets very messy. But again, it kind of either wants all of its inputs and outputs to be in the state ket plus, or it wants all of them to be in the state ket minus. And there's this relative phase e to the I alpha, where alpha is the little label we have on the spider. We also have a bunch of, and maybe just go through them quickly. So we can give interpretations to different shapes of wires. So kind of an identity wire just gives us an identity operation. We can have two wires crossing over each other, and that, yeah, implements just the linear operation that swaps the two qubits. But we are also allowed other things, because remember, we don't have to be unitary. So for example, we're allowed to have a curving wire which has two inputs and no output. And we're allowed to have a wire that has two outputs and no inputs. And so this wire with two outputs and no inputs, it's basically the partial transpose of our identity matrix. So that gives us this state ket 0, 0 plus ket 1, 1 up to normalization. So I'm going to play a little fast and loose with normalization in these diagrams because that makes things easier. But we can also normalize everything correctly if we want to, at the cost of kind of having either some numbers or some other like small diagrams floating around that are disconnected from everything else. So yes, so this curved wire with two outputs, this gives us an entangled state. And this curved wire with two inputs, it's just the adjoint of that one. So also the entangled state, but now as a bra rather than a ket. And so we can take all these things and we can compose them together. And one really nice thing about the composition is that even though I've written all these things down as linear maps, we can actually treat them as tensors in the sense that inputs and outputs don't really matter. So the inputs and outputs of our diagram as a whole, those need to remain the same. But within the diagram, the sort of all that matters is how we've connected up the different components. So for example, if we take this diagram consisting of one Z spider and one X spider, we can have kind of the wire that connects them be an output for Z and an input for X. Or we can have it be an output for both, or an output for X and an input for Z, and so on. And so we can even write kind of a vertical wire without loss of generality, because it doesn't matter which kind of how we interpret it when we try and compute the linear map that's represented by this diagram. And more broadly, if we've got some more complicated diagram, again, we need to like make sure that our inputs and outputs kind of all remain in place. But other than that, we're allowed to move around our different components as much as we want. So here, the top left wire is connected to the screen pi by 2 spider, and over there that's also the case. And over here, the top wire is connected to this red alpha spider, and over here, the top wire is also connected to the alpha. So that's all good. And yeah, again, you can kind of, if you take some moments with the recording later, you can convince yourself that indeed, like, all the connections are the same on both sides. And so that means that these two sides actually represent the same linear map. And this entire process of having these operations and why we're allowed to move them around like that, this is entirely mathematically rigorous. We can formalize all of this using category theory. Again, I've learned enough category theory to understand why it works, but I'm not kind of an expert category theorist. But yeah, I'm convinced that it does all work.
What do you mean by rigorous?
So we can, I mean, this is, so rather than just kind of thinking of these things as like being a sort of, shorthand notation on paper, we can really like define exactly like what the meaning of this diagram is as an arrow in a category. And then we can show using the theory of the category that like these two diagrams, they represent the same arrow. Or at least something that's isomorphic to each other. And so yeah, like this graphical language is really, it's not kind of just an illustration of something that we're doing, it is itself the mathematics. Yeah. And yeah, so obviously just being able to move things around on in the plane isn't kind of the most useful thing. What we also have is this complete set of rewrite rules. So these are basically, like little basic equations between different ZX diagrams. And completeness here means that whenever two ZX diagrams represent the same linear map, using this set of rewrite rules, we can transform one into the other. Not necessarily efficiently, but we're guaranteed that there exists some sequence of applications of these rules where we kind of identify a small part of the diagram that is equal to one side of one of these equations, and then we kind of cut it out, we replace it by the other side of the equation, and then proceed in this way. And yeah, so I don't expect you to remember all of these rules, but yeah, sort of one nice thing is this fact that this spider fusion rule over here. So if we've got two Z spiders that are connected to each other, then we can merge them into a single bigger spider that has, I guess it's not entirely obvious from this diagram, but it has all of the inputs and all of the outputs of both original spiders. And yeah, then we've got kind of here, we've got two rules that's kind of explore the relationship between the Z and X spiders and the Hadamards. So we can actually express the X spider in terms of just Z spiders and Hadamards, but we can also express the Hadamard in terms of just Z and X spiders. But yeah, what I should mention is that if we've got a spider that doesn't have a label on it, that's equivalent to having the phase 0. That's, it's just a kind of shorthand to leave that label of 0 out rather than writing it in.
Sorry, question.
Yeah.
Are there any constraints are you always allowed to, for example, replace this spider by this other spider, or it depends on the constraints? There are some boundary conditions that you need to worry about.
So this is highly local. You just need to know, you don't need to worry about the context. You just need to look at, is there an example of two Z spiders that are connected to each other? And if there are, no matter what else is in the diagram, you can replace them by just a single Z spider.
That's very good. And that's something that the system can do automatically, or is that something that you have to sit down and reduce your whole spider into a smaller one?
It can go both ways, right? So some of it will be people kind of sitting down and writing out these things by hand. But yeah, we do also have some automated systems that do automated reasoning using these graphical equations. Of course, the automated systems, it depends a little bit on how you've programmed them, right? So they can obviously find all the matches of one side or another of one of these equations. But if you want them to do something specific, then you need to come up with a sort of overarching strategy for what order it should apply the equations in, which equations it should be applying in the first place. These automated systems, they are very good, but they can't quite do everything. And again, as I said, like this rewriting process, we're guaranteed that such a rewriting path exists, but it might actually be very long. So even if you kind of have two diagrams, like you're not guaranteed that you can kind of efficiently find a path between them.
And is this reversible? If I gave you I'm going to use the language we use in particle physics. I've integrated out a bunch of inner particles, reduced it to some effective vertex. Is this always, there's a one-to-one correspondence? It doesn't seem like it would be.
No, I mean, like, obviously, like if you have one Z spider, there'll be many ways in which you could split it into two, right? So
yes, and the order in which you apply this reduction does matter, right?
Yes, in general it will matter, because if you apply one kind of transformation, then like some other might no longer match. So these like strategies for these rewriting systems, they are quite they can get quite complex. But for example, for the fragment where all of our phase angles are multiples of pi by 2, so we can't use this rule, we have to replace it by something slightly different. In that scenario, this is the so-called Clifford fragment or stabilizer fragment of qubit quantum mechanics. And that is actually something that has been known for a long time to be efficiently simulable on a classical computer. And also in the ZX calculus, that is a fragment that we can reason about efficiently. So there we've got a unique normal form that we can get to, and we can get to it in like a small number of steps. That is just kind of probably actually linear in the diagram size even. So for this fragment, it all works very well. We can just take an arbitrary diagram, we can reduce it to this unique normal form, and then this way we can then compare whether two things are the same. So that's nice. But in general, we wouldn't expect to have efficient ways of kind of reducing anything to some normal form, because then that would give us an efficient classical simulation method for general quantum computations, and we don't believe that exists, because we think quantum computers are more powerful than classical computers.
I mean, so there's no limitation on the number of times you can do this simplification, but you will certainly lose information, right?
I mean, you won't necessarily lose information in the sense that like the linear map that's represented by your diagram stays the same throughout. But like it depends on which information you're interested in, right? So if you start out with the ZX diagram, that's kind of a direct translation of a quantum circuit, then the initial diagram, it will be very, very circuit-like. It'll be easy to see, yes, this came from a circuit. But after a few steps of rewrites, it's not necessarily obvious anymore how you can like turn that into a quantum circuit, something that's really implementable on a quantum computer. So I guess that is information that sort of, in a sense, might get lost.
Okay, thank you.
Cool. And so some of my work, I mentioned earlier, my PhD thesis was about completeness of the ZX calculus. So I didn't prove that this set of rules is complete. That came a little bit later, but what I did prove is that we have a complete set of rules for this fragment where all the angles are multiples of pi by 2, which was the first kind of completeness result for a subset of the ZX calculus. So it's a little bit different to the rules that I've shown here, because this one, for example, isn't in the pi by 2 fragment, so we need to replace that. And this one is actually not necessary in the pi by 2 fragment either. But other than that, it's very, very close to what we've got on the slide here. This completeness proofs, they mean that the graphical language is as powerful as any other formalism for reasoning about quantum computations. And so we can really use all of this stuff to, for example, optimize computations. As I've mentioned before, the fact that these diagrams, they're more flexible than circuits, we don't have these kind of rigid horizontal wires that we can maybe slide things along, but that otherwise have to stay there. Those give us more power when we want to optimize things. But again, at the end, we need to worry about how are we going to get back to something that is implementable on a quantum computer. And so for that, we actually use a different model of quantum computing, which I find really cool. So I wanted to tell you about it. So this is the so-called one-way model of measurement-based quantum computing. And so this is an intrinsically non-classical approach to doing quantum computation. So these quantum circuits, I mean, they're called quantum for a reason because they're quantum, but they come from classical reversible logic circuits. They're just a sort of generalization of those. But this one-way model is really something that couldn't possibly work in the classical world. So the way that we do computation in this model is not with unitary gates, but instead, using measurement. Initially, what we do is we prepare an entangled resource state. So not a computational basis state, which is always a product state, but an entangled resource state on some larger number of qubits. So for example, in this example that I'm here, we want to implement a computation from 3 qubits to 3 qubits, but I'm preparing kind of more than 3 qubits here. Each of those spiders corresponds to 1 qubit that I'm preparing. And each of these Hadamard gates that connects 2 spiders corresponds to entanglement between those qubits. So this is my entangled resource state. And I mean, this is an example of a quite specific resource state, but in general, there are families of these entangled resource states that are universal, so that we can use to implement any quantum computation we might want to do. And then we do our computation via successive adaptive single qubit measurements. So I've indicated this here in my diagram by adding these kind of extra spiders. These don't exactly 100% represent a measurement. They represent one specific outcome of the measurement. But actually, for the purposes of this model to kind of represent what computation we're aiming for, that's turns out to be enough. So the reason that our measurements, when we want to implement this model, have to be successive and adaptive is that, of course, any single qubit measurement in general is not deterministic. But we want to use them to do a computation that is deterministic overall. And this isn't always going to be possible, but if we've set up our resource state in the correct way and we do our measurements in the right order, we can adapt later measurements to compensate for having seen an undesired outcome in an earlier measurement. So each measurement it's a qubit measurement, it has 2 outcomes. One of the outcomes is going to be the desired one that drives our computation in the direction we want to go. And the other one is the undesired outcome, which is orthogonal to the desired one. And so if we see an undesired outcome, what we do, if we set things up right, is that we modify later measurements in order to compensate. And this makes use of the fact that our space is entangled. And so we're actually kind of effects on other qubits can compensate and have an effect on something that we've already measured. And yeah, we might need additional Pauli corrections on our output qubits at the end, but that's obviously a lot less complicated than doing kind of full-scale quantum circuits where we need to allow a much broader range of unitary operations. And so this one-way model is a way that we can interpret a broader class of ZX diagrams and think about how these can be physically implemented than just the ones that are very similar to quantum circuits. So in general, it's actually it can be difficult to take a ZX diagram and turn it into something that looks like a quantum circuit. But taking a ZX diagram and turning it into something that looks like a one-way computation, that's really straightforward. Basically, all we need to do kind of from this diagram is we need to get rid of all the X spiders by making them green, and then we kind of fuse as many spiders as we can, and then we will be in this sort of form. And then if the computation is set up correctly, then it'll be one that can be done deterministically in this one-way model, and that then gives us both a way of actually potentially implementing that computation if we have physical hardware that uses the one-way model, which does exist, or at least will exist soon, or also there are ways that we can translate one of these overall deterministic one-way computation into a quantum circuit that we can then apply to our ZX diagram that represents the one-way computation. And so this one-way model is indeed that there exists certain hardware that is planning to use it, maybe not quite just yet, because one sort of slight difficulty with this one-way model is that it requires a lot of back and forth information transfer between the quantum side and the classical side, because basically after each measurement you need to check, was it the right outcome, what adaptations might I need to make, and that's something that is currently quite difficult. So for a circuit you can just kind of send the whole gate sequence as instructions to the quantum computer, it'll do all of those, and then you just need to do your measurements at the end, and you don't have this constant back and forth in terms of information. But for example, for photonic quantum computers, where entanglement is actually quite difficult to create, it makes sense to sort of front load that and then do your computation via these measurements. And not have to worry about kind of creating extra entanglement inside your circuit to do kind of these controlled NOT gates or other 2-qubit gates. What I should mention here is that, of course, in order for this computation to work, we can't just do computational basis measurements. So we need to allow a much broader range of measurements to really be able to drive our computation in the direction we want to go. But it's very well understood kind of what types of measurements we're allowed to make that are compatible with having something that is deterministic overall. And this one-way model, in addition to these practical applications, it also has these theoretical applications I've just explained in terms of optimization, and also, for example, classical simulation of quantum computations. So where, again, it's useful if we can kind of shrink the description of our quantum computations as much as we can, and then we can use sort of tensor network contraction methods to try and calculate sort of probabilities of certain outcomes of our computation, for example. Okay, so that was now everything that I wanted to tell you. So let me summarize what I've told you about. So quantum computers are computers that exploit the laws of quantum mechanics, and they can solve certain kinds of computational problems more efficiently, but they're really always going to work together with a classical computer as kind of a quantum coprocessor. And there are a lot of challenges in getting sort of working large-scale quantum computers. Well, we need to understand which problems they are useful for, because, yeah, while they have their applications, they certainly can't kind of improve just arbitrary computations. Yeah, we want to know how we can optimize our computations on a quantum computer and how, yeah, we can ensure that the quantum computer really does the thing that it's meant to do. We need to understand how to do quantum error correction, because it's impossible to avoid errors in a quantum computer. And yeah, so that was the overall kind of summary of the field of quantum computing. And then kind of about my personal research more specifically, there's the ZX calculus, which is a rigorous graphical language that allows us to reason about quantum computing. And it is more flexible than the standard quantum circuit notation. It has a complete set of rewrite rules. So whenever we've got two diagrams that represent the same linear map, we can transform one into the other. And it has this broad range of applications to, I mean, I mostly kind of am interested in applications to optimization, but also there are a lot of people who work on it in connection with quantum error correction, sort of representing the encoder that takes our initial state and turns it into this encoded state, and then figuring out what kind of fault-tolerant operations we can do on the encoded state. That's another application. We also use it for classical simulation of quantum computations, which is kind of really quite closely linked to optimization, because of course anything that makes our computation shorter is going to not just help us when we run it on the quantum computer, but it's also going to help us when we try and simulate it on a classical computer. And yeah, that was it. Thank you very much for your attention, and I hope this wasn't too long overall. Yeah.
So now that you've got this ZX calculus set up, and it's essentially a perfectly good abstract category,
yeah,
that means that the original matrices and vectors are now a representation of this category, I guess.
Yeah.
So the natural question is there other interesting representations, same category?
So yeah, as I said, I'm not kind of like that much of a category theorist. Obviously, yeah, I mean, the obvious one is, yeah, like this kind of category of matrices, right? So yeah, like your objects are just the numbers that tell you kind of, yeah, the shape of your matrix, and then yeah, your arrows are matrices, and then you have matrix product, and yeah, kind of canonical product.
One thing you could be thinking, I can think of several directions already that are physics sort of inspired.
Yeah.
So obviously, instead of qubits, you could use qubits or general qubits.
Yes, yeah. So there are some people who look at generalizing this. You do need to, like, yeah. I think this sort of the basic definitions of the Z and X spiders, those generalize fairly easily. The Hadamard, the transformation that goes between them, that does become a bit more complicated when you go to higher dimensional systems. And then the rewrite rules you do have to adapt as well. So I guess the spider fusion stays, but like some of the other rules have to change, and they get more complicated in general. There've also been so there are a bunch of people who work on quantum foundations, so really trying to understand kind of the fundamental differences between quantum theory and classical theory. And so there's also some toy models that come out of that. There's one called Backens toy model, which is basically a sort of a way of using a hidden variable model to kind of reproduce certain effects from quantum mechanics. And that one also can be represented using ZX calculus. But again, you have to make some changes to kind of the types of labels you allow in your spiders. But actually, the rewrite rules look largely the same for that.
One thing I was thinking, which you might be able to use the exact same rules even, but nevertheless is a different set of vectors, if you like. If you wanted to use mixed states, then your states would all be represented by density matrices.
Mm-hmm. Yes,
In principle, the same rules will apply to them.
Yeah, exactly. So that's actually a very good point. Yeah, so there's kind of one extra operator you need to add to turn this all into something that works with density matrices. Basically, in addition to having, our standard spiders and our Hadamards, you also add a sort of operator that allows you to do tracing out.
Oh,
and then you interpret each of these original components as, rather than being kind of a linear map, you interpret it as, kind of being the sort of doubled version of that map. One thing and its complex conjugate. And then, you have this extra operator that does tracing out, and it has a few equations associated with it, but they're actually quite simple. So basically, if you apply a unitary operation and then you trace out, it's the same as not having applied the unitary. So that's a fairly simple set of extra equations you need to add. So then you've got that in the same framework as well.
Thank you.
Yeah, thanks. Any other questions? Yeah.
Would you expect any unique compiler errors on a quantum compiler?
Yeah, probably. I mean, I guess there could be stuff where you want to use some qubit that hasn't been initialized yet, or something that's already been measured. Things to do with the fact that you can't copy data, right? So there's all these things that you need to take into account. Again, I'm sort of on the fringes of this quantum programming languages community. So there are people who work on developing programming languages for quantum computers, and I guess most of them have the actual computer science degree background, and didn't just move into it for the PhD. That's certainly a very active field. So there's kind of some interesting things you need to basically handle sort of separately, the classical information that you have and the quantum information, because the classical information can be copied, but the quantum information can't be. And and then obviously in compiling, as I said, one thing you might want to do is kind of adapt it to the specific hardware you're wanting to run it on and the specific gates that are available there. So I guess there's also things that could go wrong with that. Yeah.
I think you mentioned that there might be a one-way quantum computing platform coming soon. Is there some specific company or something that's working on that?
So there are companies that are working on photonic quantum computing, and I think most of them are probably expecting to use this one-way computation because, as I said, with photons, the really difficult bit is to get them to interact. And so if you want to create entanglement between photons, that's, it's useful to just be able to do that at the beginning and not kind of as part of an ongoing computation where if it fails, then you've lost kind of all the progress you've made so far. But if you do it as part of preparing this resource state, then you've kind of lost less if it doesn't work out. And there's something called fusion-based quantum computing where, you kind of combine this because of course you also don't want to or can't have your photons sort of idling for very long time. So you don't want to kind of just create actually the entire resource state right at the beginning of your computation, because then the qubits you measure last, they would kind of just sit around for a really long time. So instead, what people are planning to do is to kind of have these, basic sort of resource states that are a bit smaller, and then you kind of link them together using these fusion operations, which again, they have a certain probability of working. But yeah, if you set them up right, then you might get multiple tries. And you can kind of incorporate also some certain kinds of error that can happen during that into this standard like one-way framework, and this sort of undesired measurement outcomes that you can compensate for.
Just a comment. Your graphical notation looks right. Reminds me of Penrose's bird tracks.
Yeah. It's certainly like sort of I guess it's a bit inspired by that because yeah, like Penrose's tensor notation is this idea of you have your kind of boxes or like blobs or something that represent tensors, and then you have the wires between them that represent kind of contracting two indices. Yeah.
Are they different categories?
I expect so, yeah. I don't actually know 100% what Penrose used his tensors for. I assume it was something to do with cosmology or something.
So, it was group theory.
Group theory,
You
okay.
It fits into group. There's a book by Satanovich on that, where he goes through all group theory using.
Okay. Yeah. So I would expect
that's more general.
Probably something different, but yeah, it might. Yeah, one might be able to kind of embed one into the other in some way.
Presumably category tensor or tensor.
Yeah. Yes, I expect. Yeah, there must be some way to formalize that. Cool. Yeah. Then.
Yeah, that's everything with Miriam again. We'll close the Zoom meeting.